So next one, generate a confidence interval for a single proportion. So there's two ways you can do this. You can do this model-based, or you can do this, and you can do model-based if you've met the validity constraints, but we have to do the validity constraints slightly differently because we don't have the proportion from the null hypothesis. The proportion from the null hypothesis is indicated by this p sub 0. All right, so we have the sample proportion p hat, which is 0.106. And we have this confidence interval. We're going to do the 95% confidence interval. Now, just a footnote. If 5% is the default level for hypothesis testing, 95% is the default level for confidence intervals. Okay, we're going to use a mathematical model to do this, as well as through randomization or bootstrapping. A comment. So here's my comment. Come on, let me draw. Oh, I'm on erase. Draw, boop, draw. There we go. So if I'm doing the 95% confidence interval and I'm in the model, here's where the p hat would sit. It sits dead center. And then what happens is we're going to have 95% in the middle. And that means the area to the left here is going to be 0.025. And the area to the right will be 0.025. Now, that means that this is the 2.5th percentile, and this is the 97.5th percentile. P sub 2.5, and then P sub 97.5. And we can get these multipliers, which are the critical values, by traveling back over to jamovi. And let me click and find where I've got to go. So give me 2 seconds. I click on randomize. I go to model-based inference. And I look here, and I have 95% in the confidence interval. And I click on that, and you'll see we'll get the 1.96. So the multipliers for the confidence interval would be 1.96, but they're also the critical values for hypothesis testing. So if your alpha were 0.025, your critical value would be negative 1.96. Okay. Now let me go a little bit farther with that, because that way I said that might not make a lot of sense. Suppose your alpha was 0.05. So alpha is 0.05, and you're doing just a left-tailed test. So that means the total area in here is 0.05. Now, to make the confidence interval multiplier work to get us the critical values, what we can do is we pretend on this side there is also a 0.05. And then what's in the middle would be 90%. So what I do is I change this to 90, I hit enter, and I've got this 1.645 down here. So to the left of the middle would be, and that's supposed to be a 0, by the way, but I can't seem to draw a 0. So that's a 0. You'll have negative 1.645. And if your alpha were 0.05 and it was on the right-hand side, you'd be using positive 1.645. That's a little strange. Then let me just give you another example. So suppose your alpha is 0.10 and it's a right-tailed test. So over here, this area is 0.10. Well, pretend that the other tail has 0.10 in it as well. And then what you put here would be 80%. My 8 is not showing up well. So you'd have 80% in the middle, because 0.10 plus 0.10 is 0.20, and what's left is 0.80. So if you want the critical values for hypothesis testing, you'll put in the 0.80 and you get your 1.282. So that's your negative 1.282, and that's your positive 1.282. And since we're dealing with a right-tailed test, this is what we would pay attention to. Just a little footnote there. So whatever our confidence interval is, if it's the 90% confidence interval, this one, our multipliers are the 1.645s. If it's the 80% confidence interval, our multipliers are the 1.282. All right, hopefully that helps with that piece. And I'll just tuck this down. And I showed you a way to get the critical values without having to use the Texas Instruments 84 there. Okay, so back over to this. Your validity constraints. We don't have P naught from the null hypothesis, but we do have P hat. So what we do is we use P hat times n and make sure that it's larger than 10. And we do 1 minus P hat, which would be Q hat. And we take Q hat times n, and it's going to be, needs to be larger than 10. And since those are both larger than 10, we can proceed. And so our confidence interval is going to be P hat plus or minus, and the multiplier there would be the 1.96 or the 1.645 that we got from using our confidence interval calculator, and then calculator for the multiplier. Then we've got to get the standard error, and since we don't have P naught, we use P hat instead. So we put P hat 1 minus P hat over n, and we end up getting this 0.0046. And so you can see our computation here. We get 0.097 and 0.115. Okay, so that's our model based. Okay, and in this situation, because it's model based, the distance from the estimator to the end is consistent on both sides, and that's the margin of error. So when we're looking at our model, this piece here is the margin of error. So the z star times the standard error. And the plus or minus comes into play because you're going both to the left and to the right. And so when you're looking at the sketch that I made of the here, so you have a negative representation and you have a positive representation. So the plus or minus takes care of both directions. Okay. All right, where are we at? Next, we're going to use randomization. So we use a technique called bootstrapping here to do this. And so we have 4,387 balls in this group, and that comes from the idea that our sample that we pulled had 4,387. And we're going to have 463 red balls, so those are the successes. And let me scroll back here. So the 463 is coming from taking our P hat times our n. That's where our 463 is coming from. And then our 3,924 is coming from our Q hat times n. My apologies for stumbling there. So we have a number of red balls, we have a number of white balls. Those are successes. These are our failures. We reach in, we pull out a ball, we record it, and we put it back in. We use width replacement. Bootstrapping is doing width replacement. Okay. You repeat this process many times to build a distribution of sample proportions. This process is called bootstrapping. I said that. All right. Now, the 95% confidence interval, when we look at this, is going to include the 2.5th percentile and the 97.5th percentile. So what's going to happen is because your data sets don't always end up balancing out, you could end up with a distance from the middle to the tail on the left and the distance from the middle to the tail on the right being slightly different. Just FYI. Okay, so let me take this drawing. Let me close this out so I'm not stumbling over it. I don't want to save that, so I'm going to just delete it. And then we're going to go back here. All right, so we want to go to single proportion confidence interval. I'm going to randomize single proportion confidence interval. We need to take text ind and put it in our variable. All right, where our confidence interval is the 95%, we're doing the bootstrapping percentile. We've got 100 observations in there. Each one of those observations has 4,387 draws and so on. If we click the seed random, what we're going to get is that our lower end of the confidence interval is 0.097, so that's the 2.5th percentile, and then the 97.5th percentile is at 0.113, okay? And remember, 0.106 is our middle, and so it is the case that the distance from here to here is slightly different than the distance from there to there. It's because it's from a simulated model rather than from the theoretical model. Okay, so let's go back real quick. I believe it asks us to increase our number of observations to 1,000 to see what happens. So right now at 100, we're getting the 0.097 to the 0.113. At the 0.097 to the 0.113. You'll notice I did click on the seed random number generator, and because I did that, this distribution is going to match this distribution here. Now we're going to increase this to 1,000, and we're going to change this to histogram because the dot plot looks really weird. All right, so now our lower is still 0.097, but our upper is a little bit farther out, and it's now at 0.115. We're starting to see a thing where the larger samples, the law of large numbers, is coming into play. So as our sample sizes increases, the behavior begins to match the long run or the theoretical model, and that 0.097 is matching and the 0.115 is matching what we see here. And so the law of large numbers is coming into play. All right. Let me go back here. We've got the 95% confidence interval. Good. We're not at the spot where we can talk about two proportions yet. All right. A comment. You'll notice in this spot where it has 0.12, 0.12. So you can use confidence intervals, and in fact, it's expected that you do a hypothesis test along with confidence intervals, and you look at those together, and the hypothesis test that we did previously said we're going to reject the null. But if you notice as well that the confidence interval built off of forgive me, I lost my train of thought. The confidence interval that we built here does not contain the 0.12, and that is another indication that we're going to end up rejecting the claim, rejecting the null hypothesis, or refuting the claim. Okay, I'm going to stop here and upload, and then get the next video up.